Welcome back to another episode of Modern Day Mysteries, where I, your host, Dr. Stephen Nagov, brings you on a tour of unsolved mysteries in our modern world. Today, we'll journey through one of the most famous unsolved mathematical problems, called the Collatz Conjecture. Now, mathematics is a complicated subject, to say the least. It's filled with intricacies, arbitrary letters, and overall, needlessly complex equations. But for some, including me, math is more than just a tedious step-by-step set of equations filled with letters and numbers. Math is a beautiful representation of the complexities of our universe. And that's what I want to share with you today. We use math every day to describe how much and how many. We also use math to describe how to achieve our desired results, how fast to go, how fast a car should go, or how many eggs to buy, how much money the eggs will cost. The Collatz conjecture is one of the most puzzling math problems of our modern age, and it reflects our broader human desire to grasp the complexities of our universe. Okay, let's jump right in with today's topic, Collatz conjecture. Now, before we begin analyzing this problem on a deeper level, it's important to know it's important to understand what makes a conjecture. In math, a conjecture is a statement used to explain the outcome of a pattern or a set of equations. Think of it as a theory. They are unproven and usually created by assumptions. In this case, the Collatz conjecture makes the assumption that all the positive integers that you put into the equations will result in the number 1. You'll know what I mean in a little bit. Let's start with the Collatz conjecture. First, you must know that all mathematical conjectures and theories follow a set of rules or equations. These rules are how the numbers are manipulated or changed throughout the conjecture. So what are the rules of this equation? Or what are the rules of the Collatz conjecture? Well, the rules begin like this. Start with any positive integer. If the number is even, then divide it by 2. If the number is odd, then multiply it by 3 and add 1 to it. And repeat this step. The conjecture goes as follows. For every positive whole number, repeating these sets of equations will eventually lead to 1. But what does this mean? Well, here's an example. Let's start with the number 3. 3 is an odd number, so we have to multiply it by 3 and add 1, according to the rules, and that'll give us 10. 10 is even, so now we have to divide it by 2, and we get 5. Okay, now 5 times 3 plus 1 is 16. 16 divided by 2 becomes 8. 8 divided by 2 becomes 4. 4 divided by 2 becomes 2. And 2 divided by 2 becomes 1. Now it says that we have to repeat this step, so why did we stop at 1? Well, let's test it out. 1 times 3 plus 1 gives us 4. 4 divided by 2 is 2. And 2 divided by 2 is 1. That's familiar, right? Now it repeats like this, and it always reaches 1. Now try this with any number you can possibly think of. I dare you to. And no matter how large or small, watch as it eventually becomes 1. But you may be asking, okay, so will this work for every number? Will this work for, say, 1 trillion or even 1 quadrillion? Well, we can't possibly calculate this by hand, right? However, our computers can. Our most advanced computers have tested this conjecture for numbers up to 295 quintillion, that is, 295 followed by 20 zeros. And they all eventually lead to 1. For all we know, every possible positive whole number eventually leads to 1 when tested with Collatz equations, right? Well, not exactly. And that's the catch. Despite its simplicity, this conjecture has remained unsolved for decades and has been attempted by many mathematicians till today. Why is that? Well, just because a pattern holds true for most cases doesn't necessarily mean it should hold true for every case. I mean, we know this to be true in our lives every day. Just because we see something happening quite often doesn't mean it always happens. Now, you have to know this. In order for a conjecture to be true, this conjecture must produce the same result for every possible positive integer, which is what makes it a conjecture because it's an assumption. But wait, there are infinitely many positive integers, right? Okay, so maybe this isn't the best approach, but it's only one of many. You guys may be thinking, proof? What do I mean by proof? Well, let's take a look at this example. This is what we call a direct proof, usually the hardest way to prove a mathematical problem or conjecture. This example is a little more straightforward, however, but it's a very good starting point for understanding proofs. Because of this proof, no matter how large or how small the number, as long as the two numbers that are being added together are odd, their result will always be even. And we prove this without having to test every single number. This is just an example. Now let's get back to the main topic, Collatz conjecture. Why can't we prove that this equation is solvable? The answer is that no matter how many numbers we try, there isn't a definitive step-by-step way to prove that these sets of equations will always lead to 1. The Collatz conjecture was introduced in 1973 by Lothar Collatz. The Collatz conjecture has remained unsolved and most likely will continue to for decades and maybe decades to come. Collatz conjecture has provided us, and probably will continue to provide us, with insights for the inner workings of our universe, without needing us to have a actually look at our universe. And which is part of what makes it so fascinating. And how is this possible? Well, first off, let's take a moment to visualize Collatz conjecture. Here is a visual representation of Collatz conjecture, and these are only a few thousands or tens of thousands of possible numbers that all eventually converge to 1. However, if we look at it from a different perspective, we can say that this one single point branches out into a multitude of unpredictable streams and paths, each branch further developing their own. When we look at it from this perspective, you'll probably start to notice something quite familiar. You might see the creation of streams from a source, the flow of water, the growth of a tree, or even the expansion of our universe or our galaxy. And this randomness of Collatz conjecture just shows the beauty, the unpredictability that can be applied in so many ways to our lives. Collatz conjecture has the potential to revolutionize our understanding of math and of our world. An example of this application in math would be in the finding possible insight for other notable problems. One example would be Raymond's hypothesis. This hypothesis tries to provide us with the average distribution of prime numbers. On a number line, you can think of prime numbers such as 3, 11, or 17, but the larger the number gets, the harder it is to discern whether that number is really prime or not. Now, Collatz conjecture can also be applied by providing possible insights on patterns for chaos theory. Chaos theory is the branch of mathematics that deals with trying to understand the effects of small changes and their larger consequences, like the butterfly effect. Another way that Collatz conjecture can be applied to our real world is that Collatz conjecture can be used to test computer programs and even be used to help generate random numbers. Its application to our real world and the world of math is potentially endless. However, this isn't the only reason why this conjecture is so fascinating. Collatz conjecture embodies the human pursuit to understand the impossible. Mathematicians have spent years, and few have spent decades of their lives trying to understand problems like these. The greater meaning that I've come to conclude about the Collatz conjecture and similar problems that I wanted to share with you today is that these questions, like questions about life, cannot possibly be answered. No matter how hard we may try or how long we may think, we won't ever be able to completely comprehend or understand the nature or origin of our world, and even our universe. From time to time, we all try to understand and comprehend the world that is around us, the things that happen or things that are just beyond our knowledge that we cannot possibly understand. And as fascinating and as important as it is to be curious of the world around us, we forget about the now. Instead of providing a solution for these equations invite us to embrace a greater appreciation for the unknown. But they also remind us that we can't know every single aspect of our lives. And we can also learn to appreciate the complexities of life and take a step back and enjoy the journey, so that we can enjoy our lives more fully. Collatz conjecture teaches us to embrace the unknown. That was interesting, right? I hope you enjoyed this journey. And as always, thank you for joining us in this episode of Modern Day Mysteries. Until next time, keep questioning, keep learning, and as always, keep appreciating the mysteries of our world.